Alright guys, so we're going to begin Module 5 today with Lesson 1. Our standard is 8F1. It says that we can understand that a function is a rule that assists one input to exactly one output, and that the graph of a function is a set of ordered pairs consisting of input and outputs. Okay, our objective for this lesson is that by the end of the lesson you'll be able to analyze non-linear data sets and realize that not all situations have a constant rate, and you'll know you're successful when you can make predictions about a function. This lesson is going to go a little bit differently. We're not going to have as many examples and exercises. It's a lot of just like me showing you things and you drawing conclusions from them. So just make sure you're paying attention as we go through today and writing everything down that I write down. All right, here we have example 1. It says, suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. That is, the motion of the object can be described by a linear equation. So remember, linear means a line. Write a linear equation in 2 variables to represent the situation, and use the equation to predict how far the object has moved at the 4 times shown. So the information that it does give us is that this object travels 256 feet in 4 seconds. So in 4 seconds, we can write that it travels 256 feet. Okay, that's the one that we do know. So we're going to use that information and write an equation in 2 variables, with our x being our seconds, our y being our feet. Okay, so y equals something times x. So remember, to find m, or our constant rate, we do y divided by x. So this is just something we've learned in the past, and I'm going to fill in with the 2 numbers I do have, 256 for my y and 4 for my x. So 256 divided by 4, I'll quickly do that in my calculator, and I got 64. So m, my constant right here, is 64. So this is the equation here that I've come up with, y equals 64x, and I'm just going to use it to fill in each of these remaining places on my table. So I have y equals, well, in this case, there's a 3, so it's going to be 64 times 3. Y equals, in this case, there's a 2, so 64 times 2. And then y equals, there's a 1, so 64 times 1 for my x. Alright, I'm going to do all of these out. 64 times 1 is 64. 64 times 2 is 128. And 64 times 3 is, sorry, my calculator messed up, 192. Alright, so I'm going to fill these in. And this is just a review of things we have learned before. So this is a linear equation, which means if we were to graph this, it would create a line, okay, on our graph. What we are getting into with this unit is non-linear equations. So pretty soon you'll see that our graphs no longer look like a straight line. They're going to start looking like this. They're going to be curved, or they're going to be exponential curves. So maybe it'll be like this. And of course they could go down or backwards or whatever, but that's what we're going to get into when we start realizing that not everything is a linear equation. So this is just something you should observe, and we're going to move forward and see some new learning today in the next example. Alright, for example number 2, it says the object, a stone, is dropped from a height of 256 feet. It takes exactly 4 seconds for the stone to hit the ground. How far does the stone drop in the first 3 seconds? What about the last 3 seconds? Can we assume a constant speed in the situation? That is, can the situation be expressed using a linear equation? So we have kind of the same numbers here, right? They tell us this object is being dropped from a building, so or somewhere, let's just draw like a little building. and a stone is being dropped off of it. And they're saying that before it hits this ground, this takes 4 seconds to hit the ground, and it's 256 feet. Okay, so we do know that in 4 seconds it travels 256 feet down, but it's saying, well, was it always moving the same speed? So really think about this. If you were to drop something off of a high building or a high place, is it going to fall at the same speed? When you drop it right here, is it going to be going as fast as it will be right here? Okay? And the answer to this question is no. So what we have here is a non-linear situation. And the reason why it's non-linear is because it is non-constant. That means the rule that gets us from this side to this side, it's not going to be found using y divided by x. Okay? We cannot use that rule here. So in this situation, we would need a little bit more information to actually be able to fill this part out. We would need some different values here. But the answer to our question is, can the situation be expressed using a linear equation? No. Can we assume that this is a constant speed in the situation? No. Okay? So later we will figure out, how do we fill out tables when it's not a constant situation? How do we predict things when we don't have a constant speed in something? And how do we express this in a way that we can graph it? So that is what this whole unit that we're moving into is about. It is called functions. Okay, we're going to go ahead and move forward. All right, moving into exercise 1. It says use the table to answer exercises 1 through 5. So we have this table. Again, it's giving us x for our seconds, y for our feet. Let's just look at it real quick, observe it. Half of a second, 4 feet are traveled. In 1 second, 16 feet are traveled. So even though I increased by half of a second, or I doubled, over here, I increased by, what did I increase by? 12, and I quadrupled. Or you could say I squared this number to get to the next one, okay? Next row, I went to 1.5, so I increased again by 0.5. So this is actually what I'm doing over here. Over here, I got to 36. So what did I do there? To go from 16 to 36, I added what? Well, I added 16 to 36, 20. So you can see this is not a constant rate. What we have going on here is changing depending on every single row that we get to. One thing you should notice is, just like our last equation, we have a 4 and a 256. So maybe this is actually representing that non-constant rate that we were talking about, where the stone was falling from the building. Okay? So 2 predictions I can make from this table right here. This is a non-constant rate. Okay? And this is non-linear. It's a non-linear representation because of that. And because those 2 things kind of mean the same thing, another prediction I could make is really just using the numbers in the table at, let's see, at 3 seconds, the object travels 144 feet. So I've made some predictions based on that table. Something I don't know that I can't predict here, and I would need more information. That's what number 2 asks me. Well, I would need more information to predict the distance at 3.75 seconds, because you can see like there's no 3.75 here, and I don't have a constant rate, so I would need to know the rule for this relationship to be able to find the y value for 3.75 seconds. So at 3.75 seconds, how many feet? So those are some things that I can predict from this table, things that I cannot predict from this table. Okay, we're going to continue with number 3 on the next slide. All right, for number 3, it says, what is the average speed of the object between 0 and 3 seconds? So it wants us to find an average speed here, and here's how we do this. It says you do the distance traveled over the time interval divided by the time interval. So 0 and 3 seconds, between 0 seconds all the way to 3 seconds, these are our values, okay? So in that time, what was the distance we traveled? Well, in 3 seconds we traveled 144 feet. In the time interval, how much time? Well, it was 3 seconds. So this is how we find our average between those times. So we just do our division, 144 divided by 3, and that is going to give us our average. I'll put that into my calculator right now, 144 divided by 3, and this comes out to an average of 48 feet per second. So this object travels an average of 48 feet per second. Does it actually travel at 48 feet in every second? No, because if I look at 1 second, that's not a 48. If I look at 2 seconds, that's not doubled. 48 doubled. That's not, what would it be, 96? So that's not the constant rate. This is just the average rate. Very different, okay? Make sure you have this down. We'll move to number 4. All right, number 4 says, take a closer look at the data for the falling stone by answering the questions below. So we're just going to interpret some of this data. How many feet did the stone drop between 0 and 1 second? So to 1 second, we are right here, and we're at 16. 16 feet. Okay. How many feet did the stone drop between 1 and 2 seconds? So between 1 and 2, how much did it drop between here? So from 16 to 64. So 64 minus 16. How many feet did it drop right there? I'll do that really quickly in my calculator. I got 48. Okay. So the first second, it only dropped 16 feet. The second, it dropped 48 feet, so it's getting faster. Okay, how many feet did it drop between 2 and 3 seconds? To my third, it went from 2 to 3 seconds, so 1 second, and went from 64 to 144. So how many feet is that? What's the difference between those two numbers? 144, take away 64 in my calculator, is 80. So it's dropping faster the more it falls, right? It's gaining what we say momentum. Okay. Next one, how many feet did it drop? To 4 seconds. And we're going from 144 to 256. I'll subtract those to find the difference. And in my calculator, that comes out to 112 feet. So we'll notice that each second it got faster. It started out, it only fell 16 feet in a second, then 48 feet in the next second, 80 feet in the next second, 112 feet in the next second. So what do we notice? Well, you should notice that we are getting bigger each time, right? We're increasing. How much are we increasing by? Is it a constant increase? To go from 16 to 48, I would have to do what? I would have to add how many? Well, let me figure it out. 48 minus 16. That's 32. So I increased by 32 seconds. To go from 48 feet to 80 feet.
I increased by another 32 seconds. I'm pretty sure this is going to be my increase each time. 80 to 112. Yep, it's 32. By 32 feet. So it's increasing by 32 feet every additional second, right? Okay, so for example, 1 second, 16. 2 seconds is 16 plus 32. 3 seconds was 48 plus 32, right? So we're adding 32 seconds each time, and that's how much more it is falling, okay? All right, let's go on to number 5. All right, for number 5, we're going to be finding some averages here. It says, what's the average speed of the stone each interval of half of a second? For example, the average speed over the interval from 3.5 to 4 would be that distance traveled, right, over the time interval. So let's start with A, between 0 seconds and half a second. Well, the time interval there is half a second. And if we look at our distance, we traveled, how much in that distance? In half a second, we traveled 4 feet. So it's going to be 4. 4 divided by 0.5 in my calculator is 8. Okay? This one would be 8 feet per second. All right, let's do the interval between half a second and 1 second. So between here and here. Well, it was half of a second for my time interval. And the distance I traveled to go from 4 to 16, that would be 12 feet. So it's going to be 12 divided by 0.5, which comes out to 24 feet per second. Right? I want you to go ahead and try to do C and D. Find these time intervals. Remember, this is your formula, the distance traveled over the time interval, and then we'll go over it very shortly. Okay? Find the average for these two given problems. All right, between 1 and 1.5, I'm increasing another half a second. And the distance that I'm increasing, I'm going from 16 to 36. That is a difference of 20. 20 divided by 0.5 is 40 feet per second. Okay, check that with mind. The last one, the interval between 1.5 and 2 seconds, we increase by 0.5 for our time interval. And for our distance, we're going from 36 to 64. That is an increase of, let me do it real quick, 28. 28 divided by 0.5 is 56. So we just found the different averages for these time intervals that they have given us. And what we're going to do with this information is we are going to draw some conclusions. So we're going to compare the average speeds. So what we're going to do is over each interval, if we go from here to here to here to here, what are we increasing by each time? We have 8 to 24, 24 to 40, 40 to 56. What are we increasing by each time? Well, to go from 8 to 24, we increase by 16. To go from 24 to 40, we increase by 16. To go from 40 to 56, we increase by 16. So we're increasing the average by 16 feet each interval. All right? moving on to number 6. Number 6 says, is there any pattern to the data of the following stone? Okay, what I want you to do is look at this relationship here and see, do you see any pattern at all when it comes to this falling stone? Now our table is a little bit sideways, but that does not matter. We still have our time and our distance. So to go from 1 to 16, to go from 2 to 64, 3 to 144, 4 to 256. Do you guys notice any type of data? Okay, I'll give you a little bit of time to think about that. Maybe message me in the chat. And when you're looking for patterns, your pattern is the same thing as your rule. What we did in the last examples and exercises was we found patterns. Then you can develop a rule. And when you have a rule, you can make predictions about what comes next. So, if you don't have a pattern here, that's completely fine. That's actually what our next lesson is going to be about. But we are going to start our next lesson with this question and really try to figure out a pattern for this. We're going to figure out how to actually start finding a pattern. But if you think about what we did in this lesson, you might kind of be able to put 2 and 2 together and maybe even figure it out on your own. But we're going to move on to the exit ticket now after we do our lesson. All right, for our lesson summary today, you should know that a function is a rule that assigns a value of one quantity to every second quantity. So we'll learn more about this tomorrow. Even though you might not have a formula, you can see that they happen in real life, right? Not every piece of data we have is always going to be linear. Sometimes things are exponential or curved. So this would be a function. And we'll learn more about this tomorrow. Today was just like kind of introducing you to the concept. All right, let's get into our exit ticket. All right, for your exit ticket today, you'll see this function. It's not a straight line, right? It says a ball is bouncing across the schoolyard. That looks like a ball bouncing, right? It's like going like bounce, bounce, bounce. It says it hits the ground at 0, 0. You'll see that right here. And then bounces up, it lands at 1, 0. Again. So it hits the ground again. The graph shows only one bounce. So it bounces, goes up, 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 and then it hits the ground again. Okay? It says identify the height of the ball at the following values. So I want you to look at these values and tell me how high was the ball at 0, at 0.25, at 0.5, at 0.75, and at 1. So that is going to be the first part here. At 0, how high was it? At 0.25, how high was it? At 0.5 seconds, how high was this ball up in the air? At 0.75, and at 1 second. So you're going to have quite a few answers here. 5 answers to be exact, okay? B says, what is the average speed from the ball for the first 0.25 seconds? Okay, so remember to find average speed. This is what you're going to do. You're going to do the average distance, or the distance traveled, over the time interval. Right? So the first 0.25 seconds, that's going to be your time interval. You need to find the distance it traveled, divide those two things, and give me an answer. And then it says, what's the average speed of the ball over the next 0.25 seconds? Okay? So you'll do this twice. For the first 2.5 seconds, and the next 0.25 seconds. Okay, and you should notice that it gets faster, right? Has a higher average the more, or maybe slower, but it's not constant. And then it says, the last question, I kind of just gave it away, but is the height of the ball changing at a constant rate? We need to answer this question as well. Okay, so all in all, 1, 2, 3, 4, 5, 6, 7, 8 parts for you to answer for this exit ticket, okay? When you're done, please complete your reflection in Google Classroom and work on any missing work.